Okay, today we're going to talk about something completely different than what I talked about in previous lectures. And maybe I should therefore reintroduce myself to people who are listening to me for the first time. In daily life, I work as a consultant on projects. Most of these projects have a heavy technology component. In previous lectures and videos, and I have a whole series of sort of papers on ResearchGate. I talked about quantum physics because quantum physics is the physics. It's sort of the element that is a bit missing in when you have classical electromagnetic theory. At some point in time, you need to realize that charges are discrete. It always comes with the full elementary charge, and Maxwell's equations are written for continuous currents. So at some point in time, you realize nature is discrete, and all the physical quantities we know, charge, currents, forces, momentum, physical action, Wirkung as it's called, it comes in discrete units, most of which are given by the Planck-Einstein relationship, and then. I've been defending a sort of a classical interpretation of that, even if it's not classical electromagnetic theory, but in the sense that a lot of what happens at the elementary particle level can be analyzed as ring currents, charged oscillations with incredible frequencies at incredibly small scale. But when you think about it, it is a statistically deterministic system in the sense that we never know the initial conditions. Where is the charge at this point in time? Because it whizzes around maybe at the speed of light. But that's where the math of quantum mechanics is nice. It's sort of a totally new way of thinking about probability theory, I think. And that has been nice. But I've been talking for 2 minutes about things that I really do not want to talk about in this lecture. I want to talk about quantum computing. What is it? I will immediately add that I'm not a specialist in the topic, but professionally, I need to sort of make sure that I follow that. I think there's a lot of hype around it. The material science that comes with it is quite interesting. And so I'm going to talk about that. The thing is, I will first present a few things that you've probably also seen if you're a little bit like me, like this thing here, the announcement of what is currently the largest quantum computer, which features two things: something that is called a quantum processor. So that would be the equivalent of a CPU, central processing unit in a computer. And then what is also not revolutionary about it, but it has, well, at this moment, the largest number of qubits. Qubits are, they're logical qubits and then they're physical qubits. We talk about physical qubits here. Physical qubits are devices that can store quantum mechanical states. And you will immediately ask, what is a quantum mechanical state? And I'm with you to ask that question. Quantum mechanical states can be anything. They can be an energy state. They can be a spin state, in which case I think, it's like keeping track of the magnetic moment, the north and the south of these tiny electron magnets. It can be a linear or angular momentum state. It can be anything. And so that's the first question, which is usually not really answered in these articles, is okay, what are these bits? And I'm starting with this one because when you see sort of this IBM Newsroom article, you get very vague information. You get like here what you see, the number of classical bits that would be necessary to represent a state on the 127 qubit processor. And 127, it's not by accident adding the zero. You get at 128, 127 bits, so that would just be like 32, 64, 128 bit processor. So here we have 127, 128, 127. That's the numbers you can have. A qubit processor, so it's like a bit processor. But when I read that he says the classical bits that would be necessary to represent a state on such processor exceeds the total number of atoms in the more than 7.5 billion people alive today, then I'm going like, what is he calculating there? And I think he's indeed calculating the number of numbers that you can store when you have 127 or 128 bits that you can put. You can either assign a 0 or a 1 value, because if you do that, to the power 127, you arrive at a number that would indeed exceed or be in the same would we have the same order of magnitude of the total number of atoms in all people. It's a number with 38 zeros, so 10000 and 38 zeros. So what I'm thinking here is that he's basically just saying that this new computer from IBM, it's the Eagle processor, and it connects with 127 qubits, which serve as its memory. I'm thinking you've got something very simple here. Basically, indeed, a quantum processor. I don't know what the technology is of that. And then you have a memory, let's say, of 127 or 128 bits. That's what I see here. I may be wrong. But then I go like, okay, fine. Let's go to another website here. Do I have it here? No. Yes, here. IMEC. IMEC is a microelectronics gigant here in Belgium, not so far from my home. Physical qubits. How do they look like? So I said here they're spin qubits. So these can store, the spin. What is spin? Spin is angular momentum. Things go around in an orbit or spin around their own axis. You have intrinsic angular momentum and orbital angular momentum, and yes, we know we can store that. You see here cryogenic device testing. Yeah, often you would store. Think of a superconducting current that you want to preserve. That's in cryogenic conditions. And then, so what I'm thinking here is these qubits, especially because they are kind of bulky things. I don't think this is the picture of others. Of sort of these circuits or devices that store the spin state of an atom. In physics you have a Penning trap, in which you basically can indeed sort of store one electron in a very strong magnetic field, a quadrupolar field, and it's going to spin around, but its magnetic, its spin moment or its magnetic moment is going to be aligned with the electric field surrounding it. And so these are quite bulky devices to store just an up or a down state of an electron. And I will talk about that. Sort of these logical state, these quantum mechanical states. What makes them any different from the 0 or 1 logic that you have with normal bits, and I will talk even more. You could think quantum mechanics is all about states that are maybe not clearly defined, that are a superposition of two base states clearly defined, 1 and a 0, true and false, and then maybe you have a value that is well, we don't know if it's true or false. We don't know if it's up or down, but we can, model the probability of it being up and the probability of it being down, which is its complement, of course. So, maybe we can have some kind of three-valued logic or fuzzy logic, but I will argue that the true revolution that would come from this, I wonder how it's going to be different from what we currently are doing now already. Fuzzy logic, multi-valued logic in computer languages and all that kind of stuff. So superconducting, it's the same thing. So these are like then not tiny little magnets, because when I see about these spin qubits, I think like, what's different than the bubble memory that we had 40, 50 years ago. And the problems that we had with bubble memories, these were also like little magnets that you stored, was that, if you would read them, the reading would be destructive. And I know from quantum mechanics, it's the same thing. Spin, angular momentum, these are like, very delicate equilibrium states of charge in motion, and the slightest disturbance trying to read them, trying to see what the spin is, it's destructive measurement. So how can we cope with that? So I see the same thing here. Okay, ring currents. I said my theory and my understanding of quantum mechanics is that we are basically modeling, electrons as very tiny ring currents, not only when they're in an atomic orbital, but actually the electron itself we think as sort of some kind of core Zitterbewegung charge. That was Schrödinger's hypothesis, like a little core charge. The classical electron, which has a radius which is related to the electron, the charge radius by the defined structure constant, so that whizzes around. And I can imagine that indeed in a superconducting, cryogenic. So for the rest on this website, there's a lot indeed on cryogenic technology. I can imagine if you implement electronic circuits in a cryogenic environment, that you need to watch out what happens with your crystals that freeze to temperatures are just below 0 Kelvin. So yeah, there's a lot of technical challenges, but I don't see anything that is sort of like convincing me, saying like, wow, we're talking something that is going to revolutionize what we are currently doing, basically molecular engineering as part of the miniaturization of transistor circuits. I go to the article on Wikipedia. I start to read Wikipedia less and less. It defines qubits. It has very little information. I said it sort of states the obvious. Qubits face issues of stability, decoherence, what is probably the same thing. Fault tolerance is also, these are very delicate equilibrium situations, spin, magnetic moment being up or down, and a small disturbance or a measurement will destabilize it, so then it becomes decoherent. The quantum state degenerates, and so then you don't. So then there's errors and scalability. Of course, I said these devices. That's something I didn't show here. They build them actually apparently on 300 millimeter. Where is it here? 300 millimeter tooling. So that means the circuits they designed probably in a when I see these pictures in a rather classical way. You have a wafer, a plate of silicon, and then you have a very advanced process of lithography, basically using a light and a mask to engrave circuits on it. I will talk about that in a moment. So, but this is nowhere near, the square millimeter over a few square millimeter that we have today to integrate not millions but billions of transistors. And here we're having rather bulky things apparently, which we put on a silica plate or another plate. I don't know if it's silica, of maybe for cryogenic reasons. If it's a super cooled environment, you need something else than silicon. 300 millimeters, so that's 30 centimeters. So that's 3 by 10 or 5 by 6. Let's say 5 by 6 centimeter. That's very bulky, especially when you think of what do we have? We have sort of a processor, and then we have as memory 128 bits to our which the CPU, this quantum CPU can work with. So let me go to my notebook on that and start from scratch a little bit. one thing I always wanted to say is I've done like 20 lectures and a lot of papers on the weirdness of quantum physics, probability waves. What are they? The Broglie wave, the matter wave, wave-particle duality, how we should understand it. And I think I did rather well in demystifying a lot of things that are going on and bringing it back down to something like you can understand in terms of, I said, atomic or subatomic, ring currents, charge that oscillates. So the good news here is, I think, I looked at Feynman's explanation of how an electron actually propagates or moves in everyday language, how an electron propagates or moves through a crystal lattice. And then, there's also a lecture. He wrote his lectures in 1963. They're very good. They're very interesting. But sometimes you think like, and with how is it called, with the benefit of hindsight, which we have, we're 2023 now, do you think like, man, this is absolutely not to the point. And there's easier ways of explaining what might be going on. The way actually modern day the basics transistors really work, what happens in a silicon crystal is given here. So basically, you need to imagine that you have silicon as an atom. It has 4 electrons in its outer shell. It's going to come together in, I won't talk too much about it, I haven't looked it up. But it comes together sort of to, fill basically what you have here, and its outer electron band. As said, we have like 2 electron pairs, 4 electrons. And it's going to come together with 4 other silicon atoms to fill it completely to this magical number 8. That's got to do with you have a principal quantum number for the main energy level of an electron in an atomic orbital, an electron orbital in an atom. And then there are subshells, and then of course we know since in Fermi electrons do have a real magnetic moment, which at that scale is actually rather large, and so they like to be all together with neatly lined up magnetic moments, so as to lower the joint energy of these 8 electrons. These look like smileys. Let me erase it. So that's what we have. I want to keep my notebook clean, so I'll go back. So we have filled electron bands, as I call it, and that's called in chemistry, the valence band. Some atoms will not have fully filled valence bands, and they will basically chemically interact with other materials and form polymers or other complicated molecules or not so complicated molecules to fill up and share electrons, so the valence band is full. So what do we have above that? You probably know how Schrödinger has this model to build up the hydrogen atom and model all the orbitals around. We have unfilled electron bands where there are, these gray, there are no electrons there. That's why I put them in gray. So what happens sometimes is that, let's say we have 2 electrons, we could have 4 or 6 or 5 or whatever number, is that it gets kicked because there's a high potential on one side and positive one and negative on one, so we have a voltage, and one of the electrons wants to move towards the place where there are not so many electrons, where there's a negative potential, and so it's gonna end up here, and maybe further, maybe it's gonna, but maybe not, because maybe it's gonna kick another electron. That's actually how electrons propagate. The signal is very fast because one electron will kick another electron from its neighbor out of its orbital, and so that's where the tick 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 an electron, the signal moves, but the actual drift velocity, as we call it, from the electron, that can be very low. Maybe this electron is only gonna go 3 or 4 atoms jump from one to another and another and another, and then the potential might fall away, the voltage might fall away, and so 3 electrons will have gone from one end to another, but it's actually the last 3 guys standing in the row, so to speak, that actually move and disappear from our wire or our lattice or whatever it is. But so here we have that. So we might have an electron moving here. So let's go back. So then we have 1 electron in our valence band, and we have 1 electron in a higher energy state, which all these higher electron, all the higher orbitals, when they get an electron, the material becomes conducting. I said we have an electron that is moving, maybe not very far, but as a whole in our wire or our lattice there will be an electric current, because it's like it's really like a row of people, and at some point in time the orchestra chef says, all raise your right hand, and then all the right hands go in the air, and it's very synchronized. Move 1 step, that's probably the better. Move 1 step to your right, and so then the whole row moves 1 step to its right, and think about it as that. We have electrons that were stationary, now they're no longer stationary. So that's basically what happens. An electron moves from in the valence band to the conduction band, and you can have all kinds of situations. The other thing that I need to say, like once it moved from a valence band, we have a hole here. There's no electron anymore, and this electron would have loved to stay with its friend, its buddy, but so it will welcome, and this is the other thing, from another electron, it will of course welcome another electron to fill up that hole. And that's basically all you need to know to understand semiconductors, and actually all you need to understand, let me clean up, I can. In between the unfilled electron gaps, the conduction band, and the filled electron bands, the valence band, we will have what is called the band gap. It's the difference between the the energy of the conduction band, and the lowest energy level that you need to reach to get into the conduction band, and the highest available level in your valence band, where the electron in the highest state. If this one is empty, then of course you tap the next level. So if the energy gap, basically I'm simplifying a lot, but it's not a bad simplification. If the energy band is very large, a lot bigger than 0. Now we have insulators, electrons. You may apply a voltage, a differential between plus and minus. Really imagine a crystal, sort of a solid piece of material, a solid piece of silicon. In this case, we're going to talk about. Then you have an insulator, and actually silicon in its pure state, when it's pure silicon, it actually is pretty much an insulator. It conducts, but only very little. And this is why we're going to talk about doped silicon, the kind of doped silicon that is used. Dope, think about drugs, but don't think about drugs. But it considerably increases the conductivity of silicon, because silicon, actually, I want to quickly say that silicon is a really it's a common thing. It's in sand. I think it's 27% of all solids on Earth are silicon. Silicon in various combinations, and the funny thing is actually silicone rubber. I would need to think it's with I don't know, with other atoms, but that's a polymer which basically consists of silicon, but really acts as an insulator, is also used as an insulator, has a lot of other uses. And when you see silicone rubber and you see a silicone crystal that is used in a microcircuit, an electric circuit, then you will say like, whoa, these are like two entirely different materials, which is often the case. Carbon also comes in so many varieties in nature. It can be diamond or it can be coal. It all depends on in what kind of crystal structure it comes, and with other elements it combines. So very large band gaps, clear insulators. The electrons in the valence band. I'm not sure what is not working. Okay, my pen is dead. Then if these electrons are tightly bound, then we have insulators. It works again. It was a color red, that's why it didn't show up. If the band gap between the conduction band and the valence band and the bands within those, but the highest and the lowest one, is sort of larger than zero, but not very close to zero. That of course depends on what is large. Then it's going to be a semiconductor. What is large? What is small? Well, what is the voltage you're going to apply? In microcircuits, like 1 volt, 1.5 volt. If you apply 200 volt, that's something different. But let's say that semiconductors, you need a lot of energy, kinetic energy, potential energy to kick electrons out of the valence band, and the conduction band. There will also be a lot of let's say the equivalent of friction, the electromagnetic equivalent of friction. So you don't want semiconductors. You don't want to use that for transporting electricity charge, because it's going to heat up, and all kinds of other things are going to happen. If it's near zero, then we have conductors like copper wires and other conductors, but basically metal. Semiconductors are often also called semi-metals, but that makes you think of metal, so I prefer semiconductors. So I've been talking too long already on something that is quite simple. I want to talk now about really silicon transistors and integrated and chips. Really, so you have a silicon chip. I said there's a piece of silicon. It's a chip, really. A chip is just a piece. Chip, think of something chipped off a rock. Silicon chip doped with phosphorus. That will mean that actually, in each crystal cell, there will be one phosphorus atom. So here, I think there's one phosphorus atom for every 5. We probably replace the silicon cell or silicon atom at the center by a phosphorus atom, and that has an extra electron. Its shell is full with, let me choose another color here. Its shell is full, and now we have a crystal cell with 4, the silicon. Now we're thinking of a crystal cell, and because of the phosphorus atom, we have an electron available for conduction. That really acts as almost a free electron, which can sort of walk through zip through the zip. Walk, I said, can push other electrons in the nearby crystal cell and the conduction band of the nearby crystal one place further. And so what I said, it's like this dance. Everybody moves one step right or one step left, and we have an electric current. We can also do the reverse, and that is actually doped with boron. Boron has only 3 electrons in the outer cell, so we have 3 electrons, and so we have a hole. A hole which will, of course, welcome any electron that would happen to circle around. And so if at the beginning of the current we apply, a voltage potential, we have a source of electrons, then we can fill the holes. But the holes won't stay filled because there's a shortage of electrons at the other end. That's here I'm drawing a diode, and I will come back to that. But you can sort of see what happens. We have electrons moving from a source of electrons to a place where there's a lack of electrons. And if you have holes, or you have free electrons in the silicon crystal, it doesn't matter. It will work sort of the same. We will have a current. Well, it's not exactly true, but I could sort of say that, an N-type crystal, and we have a P-type crystal, and we have silicon doped with boron, and a silicon doped with phosphorus. And so these will then become semiconductors, actually conduct electricity pretty well. The interesting thing, and that's what used in electronics circuits, is when we start playing with with both. Here I show a diode. It's a very simple thing. It's a piece of crystal. One piece is has a boron in it, and the other piece has a phosphorus in it. And we just glue these together. There's a contact surface. While glue, we press them against each other. We make sure that they bond. There's no special material to separate the two. It's one crystal, one silicon crystal, but it is just in its structure, its crystal structure. One side has the p doping, is of the negative type, because there's a free electron, so that's why we call it N and negative type, and the other one is of the positive type, the P type, but it's one crystal, just two different configurations or dopings in the material, and we push them against each other, and then we apply a current. This is not the conventional direction, but the real source of many electrons, and we have a conducting, and think of a piece of copper, or you may be surprised, but actually connections often on microchips, often they're gold plated, which is interesting. It doesn't explain their value, but part of it, there's gold or copper or whatever. But think of a little thing inside a microchip, so to make sure that the electrons can run free to the crystal and can run to the place where there's through the N crystal, where there's a place where there are not so many electrons, where we have a positive voltage. What will happen, this is the funny thing, is that this will be already like a tiny circuit where current can go only in one direction. This is how the current will go. Why is that so? Well, you can see that. Think about it. There are here free electrons. We add more electrons on one side. The free electrons here will want to go to the place where there is no electrons, especially because there are holes. In the N-type, they will want to fill the holes in the P-type crystal, and they will push the electrons that are there in the N crystal to the plus side. Reverse, it doesn't work. Why not? If we would have a minus here, well, in the N-type crystal, there are already too many electrons. There are a lot of electrons, and they're sort of loosely held in place. But if they go anywhere, they will join the source of negative electrons. So yes, it works, and we have a current in this direction. If we have a negative source of electrons here and shortage there, but it doesn't work the other way. No way. That one. So that's how a diode actually works. It's two pieces of crystal, and you can look that up. It's in the 50s or even earlier. These things were made. And I'm showing here a very simple circuit, because you will say like you're getting very bored and boring, and well, you're getting bored and I'm getting boring. But I will show you, like, you can already apply this thing and build a little circuit if you have 4 diodes that are connected like this. This is called a bridge, because you're gonna have like a wire that goes to the middle of this circuit, and then instead of the end and the beginning or whatever. So it's a bridge, called a bridge rectifier. And this, if you have here an alternating current, then it will convert this, because the current can go only in one direction. If this is plus and this is minus, then it can go there, it cannot go there. And if it's minus here, and so it alternates between plus and minus, that's an alternating current. Then from the minus it will yeah, okay, here I need to say something. This is where it's important. This is the conventional in conventional engineering. Believe it or not, current goes from plus to minus, where we know in physics you know, it's actually going the other way around. So actually, you need to think here of a minus current, and this one of a plus current. So this is a real bridge that you could buy and can still buy. I made a nice drawing here. I mean, I like it in the drawing. A BR bridge rectifier 82D circuit of I don't know which firm, with the four little wires that come out of it that you can solder onto a board, and here indeed, you know, in the middle two you will apply an alternating current and you will get a nice plus and minus output on the outer ends of that thing. So that's just to illustrate how you you know, can build things with these well, what we have here, a diode, but there's a lot of other components. What I want to show is this here now. Is a logical circuit. But before I go there, I want to illustrate once more again how it works. I shouldn't explain this. This speaks for itself now, actually. We have a diode, and what happens if you apply a voltage, a positive voltage here, then we will have, you know, a current in milliampere, measured in milliampere here, and it's called the forward bias of the diode. We will see a milliampere current, and it goes up very, very steeply. You know, an ideal diode will not have a lot of resistance, and, you know, for a small voltage have a fairly large milliampere current. Or we're talking integrated circuits here, so it's indeed milliamperes and volts of like +1 or +1.5. That's why you need a transformer on your computer. But yeah, if the voltage becomes negative, then you know, you should have no current, which is what we show here. The current gets blocked. Of course, no material is perfect, and if the force becomes really enormous, like a negative force of -50 volts, then you know, you will burn the whole thing. Basically, the circuit will break down, and the electrons will be ripped off their valence bands and move through the material regardless, because the potential difference is so enormous. Now back to the logical circuits. If we have here, you know, we can apply a current, or we cannot apply a current. So we have a 1 or a 0 here. Here's the same thing. At this gate, let's say, we can apply a current, a voltage, or we cannot apply a voltage. So what's going to happen? Well, we have a logical circuit which is called P or Q, an OR circuit. And we have a lot of, you know, and exclusive NOR and other things. Sorry for the noise. My wife is cooking in the kitchen. I hope you can still hear me clearly and that there's not too much background noise. But that's a circuit, you know. With this circuit, it's a very simple one, 2 diodes. If there's you know, a voltage applied being to one of these 2 gates, then we will have you know, a voltage here. You know, in reality, you will have a resistor to cause the voltage drops. The current needs to go somewhere. But that's actually the circuit. And let me clean up, because I want to keep the notebook clean this time. So you can think of these 2 inputs at the 2 gates as 2 bits. A 1 1 gives a 1, 1 0 gives a 1, 0 1 gives a 1, and 0 0 only when there is no voltage to neither of the gates, then we have 0. So this is really interesting. We then need to sort of say, like, okay, this is a logical state itself, P or Q, depending on the input state, let's say, of P and Q. This is why I like the word state rather than bit. We have P or Q, and we can represent this state by 4 bits. And so how many states can we have? Well, if we have 2 bits, then we have 2 possible situations. But if we have 4 bits, then we have 2 to the power 2 possible situations. We can have 0, 0, 0, 0, 1, 0, 1, 0, 1, 1, 1, 0, etc., etc. We, in this case, when we have 4 bits, we have 2 to the power 4 possibilities. And so these conditions, they're attributed, these logical states, the whole thing with the truth tables, as they are called, and how you link them to these logical 4-bit states, is attributed to Wittgenstein. I think it was earlier Peirce talked about it at the end of the 19th century about two-valued logic and all that. But in any case, we have 16 states represented by 4 bits: false, true, and, or, an exclusive, or, a not and, an exclusive, or, imply, not imply. We have interesting one also. We don't care about a value for Q. We just want to have not P. If P is 1, then the logical state will be 0, and all the other 3 bits are 0. And the other one is, of course, not Q. So it's been too long ago that I looked at this. You can look it up on Wikipedia. You can have 4 bits representing 16 logical states. That's why I said, what is this thing with 127 qubits representing a number that is larger than the total number of atoms in the 7 billion. It must be that. It must be 2 to the power 127, and then okay. So what? So what do we do with that? In computing, we do, of course, this. We have these operations, logical operations. We showed we can equate, these circuits that we can build, that depending on the value of P and Q give another value. We can have, let's call it a 4-bit instruction set. We load an operation, an AND and an OR operation in a processor, and then we take the 2 values from. And here, this is interesting. Of course, we need to store a bit. This P and Q, we can't be manually, applying a voltage to the inputs of a transistor. So we have memory cells, and this is what I said. The early memory, that was something difficult to deal with. Computer processing units were sort of invented first, I guess. But how do you store bits? How do you store values? Early storage devices, and some of them are still, relied on magnetic storage. So you have a mini magnet. Think of some kind of tiny metal structure where indeed, you magnetize the material, and like that you keep track of, is it magnetized or not, and that's the 1-0 state. The problem you have there is indeed sort of, when you read that memory, usually, you're gonna slowly erase that memory, or even quickly you're gonna have a destructive readout because you're reading messes with the magnetization of your memory cell. So in modern days, we use MOSFETs, metal oxide, semiconductors, field effect transistors. That's the full name of it. Honestly, I explained you how a diode works with crystals. This is a lot more complicated to show how a MOSFET works. It's an integrated little circuit, solid state drive. It's called solid state device because in the end it's like a chip, flash memory. It's a chip on a plate of silicon. But that's how we do it. So the memory problem is resolved. That because memory is a lot cheaper now than it was. It used to be hugely expensive memory, but the price has come down. Now we can store gigabytes and terabytes on our computers. Even a home computer now has usually, if it's a little bit of a decent model, a terabyte solid state drive. Memory is quite cheap. I'm saying quite cheap because I will talk about prices of CPUs in a moment. So then, with these simple, what we did here is said, okay, we have a memory to store, P and Q, and we can change the value. We could feed it back. We have instructions or logical operators operating on these things that are in memory, so that we can store that somewhere else. So we have here basically the logic of a 4-bit computer. 4 bits are called a nipple, a semi-octet, a half byte, a hex digit. Why? Because I said we can store 16 states. 16 numbers. That's why it's called a hex digit. We count from 0 to 10, but in computers we often going to use 0, 1, 2, 3, 4, 7, 8, 9, 10. Well, not 10. A, B, C, D, E, F, which are going to done. The A represents 10, and the F represents the 16. Why do we do that? It's easier to we work with like 8-digit octets in computer technology, and so hexadecimally expressed addresses to count and see where what is usually easier. That's a bit of a fuzzy explanation, I realize, but I think you understand what I'm talking about. So in the beginning, that was it really. The first CPUs, one that I show here, it was a 4-bit processor. They were used in electronic calculators, which were the first computers, really, just adding machines, multiplying, dividing, maybe more complex operations based on them, exponentials, etc. And that was sufficient because one nibble, 4 bits, that can hold 16 different values, so that's plenty to store a decimal digit, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. And then, store that, and then the second digit in your larger number, 200 or 1000, you store that in a separate place, and then you can, you can have registers. So you can build sort of your numerical system, decimal system, with one nibble, and you have plenty of place, 6 places left to store, for example, a plus or minus sign, or -1, -2, whatever can be useful, or maybe a reference to one of the 16 instructions or logical operations that you're going to apply to it. So you can have a register for the number, maybe 10 bits reserved for that, and then the remaining 6 bits can hold an instruction. I mean, there's plenty of possibilities, and that's how actually the first it's sort of in history, there may have been prototypes for that. The Intel 4004 CPU was designed. It had an instruction set with 46 instructions. So think of that as 46 operations, logical operations, but also numerical operations. There are a number of operations, or maybe you want to swap bits or do a mirroring on your bits. So you can invent more instructions than those 16 logical instructions. And these were stored, in 8 bits. So each had an 8-bit code. 12-bit addresses, so you could add a lot of memory. That was done with Intel 4001 memory chips, which could store at that time 256 bytes. So now and then kilobytes came and megabytes, and now we're in the gigabytes and the terabytes of a random read-only memory. That should be RAM, actually, random accessibility memory. So these 12-bit addresses could address, and that's what you see here, actually, 1404. Where's the 404 chip? Here at the center. Would work with a few memory chips. Now these are all integrated onto a really tiny IC. And then the 4003, I don't know whether that's maybe a bus to control the printer, maybe, because these calculators often had a printer. And for the rest, you see quite classical circuits with the capacitors, with the resistors, and so on, that look like they looked in your grandfather's radio. So this is very interesting because it's like a nice picture that shows how the old technology of capacitors, resistors works together with the first modern microprocessor, the Intel 440004. I hope you find this interesting. I find it interesting, so I talk about it. When you opened it up, this thing, you could really see it was a printed, a silicon chip, and you can sort of see, I don't know if you can see it, but you can see there are circuits on that. These were etched onto the silicon chip in pretty much the same way as the etching is done now. The little copper or gold. I don't know what they were. Well, copper or gold. No, really, the conductors within the crystal that were created by a lithographic process. The logical structure here of that processor, it had all the ingredients of registers that are there, what was in memory, and what had to be fetched from the memory, and after an operation was performed, where the result of that operation would be stored, so these registers, and so on and so on and so on. It's pretty, I said I'm not a specialist in that. We've moved on from that. Maybe some technical details and also sort of commercial or business detail. At that time, that chip costed $60. Which is now about $450, and it's interesting now that for a good Intel Core or a Neon Core CPU, you will pay about that price, $450. So the price of CPUs in real terms has actually not come down, but of course the quality, their capabilities, has greatly increased. It was we call large scale integration exactly because of this. Here we have a low scale integration, things that are soldered onto a board, a motherboard. I'm sorry, there's a fuzz in the street with cars honking, a traffic jam. I don't know what's going wrong today. Saturday evening, it shouldn't be busy in town. But I hope you can hear me. I will carry on, soldier on. Using MOS, metal oxide semiconductor technology, silicon gate technology. Interesting that the MOS technology, sort of that etching technology, was described as a 10 micrometer. As you know, we're now talking about 2 nanometer. CPUs have a clock rate. How many operations, which sort of the maximum number of operations, the clock that keeps, it ticks, and with each tick, an operation can take place in that time interval. It had a clock rate of 740 kilohertz. Its original design was 1 megahertz, which was not bad. But because a lot of systems that came later also had sort of the same order of magnitude in terms of clock. But that's sort of it. This is a general purpose central processing unit integrated on one single chip. I clean that. So where are we now? You know where we are now. Several generations. These are like the last generation, the Pentium Pro. Even the younger under you should remember that. 5.5 million transistors on, something that was quite small, a few centimeters. You can sort of see here also, this is why I have the picture that, it's really circuits. This is not, you can see it's gold. It was connected to the motherboard by pins. That's not the case anymore when you look here at the newer Core, Intel Core processor. But that sort of, it went from, now we are having this here, what you see here is a die. These are pictures from Wikipedia. I should acknowledge the source. A die for a very large scale integration, the very modern chips, which will put not 5.5 million transistors on one chip, chip here, but billions, literally billions. So clock rates and all that, because you have so many components which are very near to each other, can communicate very quickly with each other, at light speed, and the distances are micrometers. So we have now gigahertz instead of megahertz clock rates. The record currently is 9 gigahertz, I think. I looked that up, 9 or something like that. What modern processors are multi-core, so you have like 2 processors built into one, or 4. Modern servers will have processors. They're called Xeon, which will have up to 56 cores. That's very nice when you have a multi-user system, when thousands of people, think of the internet, need to log on to the same uh, service in some data center. So then you can have multiple CPUs dealing with them and allowing them to do what they have to do with the system. There was briefly a Xeon Phi, well, briefly, not so briefly, 10 years, but it was retired, which had up to 72 cores. So then you can do what is called multi tasking, multi-threading, basically. Have a lot of threads, conversations. Think of conversations going on with a lot of users, and you combine that with the time sharing. Even if you have 56 cores, and these are like 56 telephone lines, but you can, on each telephone line you can put 1,000 users, because these users are not so fast as the computer, and so you can, without them knowing, do time sharing on that telephone line. I'm laughing a bit, but that's how I explain things to people who don't really understand how these things work. Gigahertz clock rates. Maybe that's one thing I want to say about it. That's a lot, but it's nowhere near, the electron clock speed, or the frequency of really high energy photons or gamma ray radiation, which is like 10 to the power 18, something with 18 zeros in place of a billion nine. So I'm done, actually. I see my wife is gonna leave. And stop working in the kitchen. So maybe I should say goodbye to her. No. The issues with very large scale integration, this is again where I want to make a bit of a connection with my previous papers, which I haven't done. Like, I will start talking about quantum mechanics. They often talk about that when you read these articles. Oh, quantum tunneling is taking place. An electron is going where it shouldn't be going. There's a barrier. That problem of quantum tunneling is no mystery, and it also occurred at larger scales and in the past. You should think of what goes on inside of a crystal like that, where you have nuclei and electrons combining in a lattice structure, a crystal structure, as there's these charges that are moving. They create like dynamic fields, potential and magnetic fields, electric and electrostatic, electric fields and magnetic fields. But these are not like, these are like a wall. Well, they're not like a wall. They're like a very special wall when, on average, the potential, the energy barrier is high. It will be like a wall in which you see still, places that get, because it's dynamic, potential goes up, potential go down. So think of a sort of a wall in which the wall is there, but there are like holes in it appearing, and these holes close again, and they pop up in other places. So if you are lucky, it is like another comparison I often make is like, think of a propeller that is rotating at high speed. That sort of creates a density in space, and if you fire balls at it, then the balls cannot pass through it. Well, but if their velocity is quite high, or the energy is quite high, or comparable, then think of bullets coming out of a gun. Some of the bullets will hit the propeller blades, but some of the bullets will will go straight through. So that's how you should think. So quantum tunneling is not something mysterious, but yeah, it can cause a problem when an electron goes where it shouldn't be going. Electromigration is sort of this problem, but magnified, that applies to the nucleus. The nucleus becomes like an ion, or the atom becomes an ion when it loses one. So despite the atom or the ion being very, very heavy, having a lot of mass, it might be attracted and move its position in the crystal. Copper wires have that also. That happens at larger scales. Is that when a lot of current goes through from time, after a while your crystal structure might get damaged, might not be regular anymore, because you have ions that are being torn out of your lattice structure. So I would say these two problems have always been there, and it's not necessarily any worse. Well, that I shouldn't say. It is worse because, and this is the thing I want to end with, is what is happening with this very large scale integration is we are indeed down to the nanometer level, which basically means this is I would say the engineering precision, because the gates and all that and the components, there will be more of the order of like 50 nanometer. But so having 50 nanometer technology, which is referred to as 2 nanometer. I said this is the engineering precision. 50 nanometer is actually the size of a crystal cell in your silicium chip. So what we can say is that we reached probably somewhere, I talked about the doping in each crystal cell. And to do that, you need to have very pure material. In each silicon cell, we will put, a phosphorus atom, or we will put a boron atom to dope it. Well, I don't know if I cannot imagine if we are now at the scale where we are doing, really molecular engineering and building circuits or connections and gates that are, just one crystal cell wide or long, then I don't see how we can bring it down. So Moore's law has played out. Roughly every 2 or 3 years, you had like a halving or a doubling, I would say, of the precision. And so between 1968 and 1971, I said it was 10 micrometer. The first transistor integration on a chip was in 1968. That was 20 micrometers. When I did that, I took the values on Wikipedia and I put them in Excel. And between 1968 and today, we have reached that scale where we're really engineering, molecular engineering, building chips that actually do work, that are just the size with circuits that are and gates that are just the size of the crystal cell itself in the silicon. So I find it amazing, and I wonder, and that makes me thinking is. People always say that the trend doesn't stop, and where things are getting smaller and more powerful every day. It does look like that now we are 2023, 2025 with 2 nanometer technology. I don't know how far you can bring it down. 1 nanometer, half. Then stuff will not probably work, not as you expect it to work, because you're working like with half a crystal cell instead of with a full one. And then this game here that I explained, electron bands that are filled and serve as a valence band at the level of a crystal, and then energy levels, molecular orbitals that serve as conduction bands, that will not work anymore. We have a different system, part of a system. Okay, I'm almost at the end. The thing why I talk about these things is, if I go back, computers work basically, the logical components of a computer, I would say, is an instruction set. Okay, we said the first one had 46 instructions. Now instruction sets are much more complicated. We have you will know that basically 2 instruction set architectures, ISAs, or we have complex instruction set computers and reduced instruction set computers. The second philosophy is to be more generic and do more operations, rather than having a very complicated machine language, a set of instructions. And this is machine language. But we have, instead of 8-bit instructions, 30-bit instructions, where you can imagine part of it might be values for registers, or we can have 2, 3, maybe 4 values that we can operate upon, so we can have much more complex operations. So that's where we are. I can assure you, machine language has a lot more instructions than just 46. We have said the first chip address could, the address could only be 12 bits. So that also defined how much memory you could address. Now we have 32-bit address buses as a standard, and with these 32 bits, you can put a lot of addresses in there, a lot of places where you need to find a byte. And our data words, I said, these for these first calculators was 4 bits, basically number. Now we have 32 64-bit data words, as it is called. And I'm concluding with that is because I see that expanding. Maybe the next generation will be 128-bit data words, and maybe when it's more efficient, that's not sure. We move away from these 32-bit instructions to 64-bit instructions, and we can address a lot more memory if we would expand. Build address buses and say like, okay, we're going to use 64 bits to to define an address in memory space or on the planet. And we're on the internet, an IP address. So that is going to go on. And my question really is, how is quantum computing going to change that? And I'm going to end here and just refer basically to 2 papers I wrote in between, my 20 quantum mechanics papers, which get a fair number of downloads by probably a different public than you, if you are still listening. Here I want to address myself a little bit to computer scientists and say like, yeah, the logic, I said we can talk and chatter about, quantum mechanical states, but in the end, they're going to represent a logical state, truth or false. And in this paper, you can say like, oh yeah, but the quantum mechanical states are different because we can have superpositions of states and with the probability amplitude associated. I'm going like, okay, then you're talking about 3-valued logic basically, +1 state, and then it's opposite -1, so something is false and something is true, and then in between, well, we don't know, or either it's false with a certain probability, but then you need qualifier, but say a simple 3-valued logic, fuzzy logic, or whatever you want to call it. We can do that with our current computers. In fact, that's a lot like that, where we use, where we define a variable to have, 3 or 4 or 5 possible values. So 2, 3 n-valued logic and fuzzy logic. No, there's nothing new in, I would say, the hype around quantum computing that tells us this is going to be executed drastically more efficiently than with our old, our brand new computers. So the logical architecture also of a quantum computer, the one I showed you from IBM there, I would like to see what is different in terms. Okay, you have a CPU and you have qubits, and so these physical devices are actually very clumsy as compared to MOSFETs. I do not really see how your cryogenic qubits kept at sub-zero temperatures, and all the problems we had with the indeed memory storage and memory reading being destructive because we stored it as magnetic, tiny ring currents. When we read it, we changed it magnetic moment, so we have a destructive reading of these bubble memories. How are your physical devices going to solve that? And that has nothing to do with that has something. You can couch it in terms like decoherence and all that, but it's basically an old problem which I don't see how you're going to solve. There's a few other annexes to this paper where I talk about spin coupling and the basic concepts in quantum mechanics as relevant to maybe some kind of new logic. I don't think so. I wrote another paper also on logic and artificial intelligence, because sometimes you see that, especially in popular science, like, oh, well, artificial intelligence requires a lot of more, computing power and a different logic. again, I think the key to understanding the language model, as they call it, that are now used in what is actually a subfield in artificial intelligence. You have machine learning and a lot of fields in artificial intelligence are usually a rule based on formal rules, and then some learning that is also based on rules. But artificial and general intelligence, imitating how we humans think and make decisions. The key to understanding AGI is indeed understanding that, we have formal logical systems, and then sort of, a whole different set of rules that we actually are uncovering, also thanks to AI, that we actually use for sense making, new associations, and what I call human problem solving, and then, solving statements like the one I put here. Was Napoleon good or bad for Europe? This is we could call it fuzzy logic. There's no real answer for that because we don't have the alternative history, and so then you start arguing like, yeah, Napoleon left behind a rule-based system in Europe, and the Codex Napoleon. So for law, he was very good. And I'm from Belgium. Belgium would not have existed if the Napoleonic Wars hadn't happened. So I must say, yeah, he was good because I'm a Belgian and I like Belgium, and so on and so on. So a question like that, was Napoleon good or bad for Europe? That requires a totally different logic. Now, the thing here is also that I don't see how quantum logic is going to be, revolutionizing the way we now think this different logic works. As you said, chatbots, they've progressed, they've come a long way. So what I see is that these language models, these fuzzy logic, working with association and going on the internet itself and dig for information that might be relevant, and then sort of prioritizing it or giving it a certain truth value or probability value of being true or not, and how much and sort of the thinking about what we should be doing and what we are doing, and making an informed choice and thinking our choice through, and then having the computer, or have the computer do this, say, you should stop smoking, and we then don't stop smoking. I'm saying that thing because I want to stop smoking, and it's not easy, I can tell you. But so these thinking and human problem solving, and we want to do this, and what can we do or what should we be doing to obtain that kind of result? That's come far along in those systems. It's scary in ways. I'm not scared about it. I don't think we should regulate AI except for military purposes, perhaps. But if we regulate the civil side of it, military are going to explore it anyway. They're already doing that now in the drones, in the war with Russia. So you're not going to stop artificial intelligence as usual. The military are going to continue to drive it. So regulating it in on the civilian side of things is a bad idea, because then technology usually comes from the military sector. It takes a while before in the civil sector adopts it, and then it contributes to society. It's not a good idea to regulate AI, but I'm not here to talk politics. I'm asking this hard question: how is quantum computing? How is that going to change? The logical model that we've used over the past 50, 60 years, even longer, to build our currently very high performance computer. I have two computers here. One is an NV, an HP. Another one is an older one. I'm from a time when we had a 64K byte Commodore computer. My NV has the power of a mainframe I worked with in a job 20 or 25 years ago. It's enormous. It's huge, and it's sitting here on my desk, and it cost me like €1,000, a bit more. And I can put a virtual machine on it, and I'll do in Unix or Windows. And quantum computing, as you see it, is bringing a number of clumsy devices, and everything I see, and then I go back to the articles, Wikipedia, these 100 Eagle quantum processor. I do not see really where that technology is going to bring us, except, of course, what I do find interesting is, and that's why I'm a supporter, of course, is I see IMEC, and I love IMEC, is making very nice things. And, of course, it is it is for an engineer, it must be challenging to sort of get that, like, why can you build a cryogenic information holding device, and then a CPU that works in sort of the same way, and then can we have a look at indeed the magnetic moment of electrons, and maybe use connections that work with light particles, photonic connections. All these kind of things are very interesting from an engineering point of view, I would say, but from a computing point of view, I am not so convinced, and I'm gonna check. I've been talking for an hour and 15 minutes almost, which is long. Um, I will upload this video. I don't know if it's interesting for me. It's part of it is actually exploring my new Wacom tablet, which I adore. This bamboo paper is the first and simplest application of it, where I can insert images, where I can write, and where I can use like a whiteboard on my desk to try to explain something, ideas, and this is what I did. So this is a bit of an educational experiment for me, I would say, and also I know sort of I'm currently looking for a new project, and when they see my lectures on quantum mechanics, they go like, "This guy is way out." And I hope this lecture shows that I do know my stuff when it comes to information technology, and that my thinking about fundamental physics is not unrelated to the everyday questions that I have, and how does this work. And so maybe next time I'll do a lecture, I don't know, on the smartphone, or the most fascinating thing I think is distributed computing. The browser has become the computer. We know that. I'm not talking about social media only, but the way we build systems, and that's fascinating. I'm a certified programmer, both on the back end and the front end of these things, where code get executed, the cookies, how that works. Another reason why I'm doing these lectures is actually I wanted to maybe promote them using Google and YouTube. And so I want to know how social media marketing works, and that's, I must say, I'm looking at it. It's fascinating, how your actions get converted into going to another video, or buying something, or looking at this is fascinating. And so that's another reason why I do these videos, to learn, and to think, and to try to work through basically questions I have. And as you can see from this session, to a lot of questions I don't have the answer. I'm just thinking that some things make sense and some things make much less sense when trying to work towards some understanding of the hugely complicated but also incredibly beautiful world that we are living in. And that will be it, folks. The Looney Tunes. That's all, folks. Well, that's from cartoons from the 50s, so I'm really talking as an old man now. But that will be all, folks, and hope you listened. If you're hearing this, then you did, and I want to thank you, give you a big thank. Like my videos, attract some more traffic to it, because in the end, I do want to be read. And these kind of lectures also, if you have suggestions,